Hey guys, so this is a little video that hopefully will help you with the calculations for the Hess's law portion of the thermochemistry lab, Chem 101. So the three thermochemical equations that you get from your experimental data are: one, the heat of solution of citric acid monohydrate, this first guy right up here. The change in enthalpy for that reaction will be the heat of solution for the acid. The heat of solution of solid sodium bicarbonate, the second one right here, and the reaction that you perform between sodium bicarbonate and citric acid ends up being in solution, this third reaction right here. Now, what has to happen for this reaction to occur is that first the citric acid monohydrate has to solvate, has to be dissolved, and so does the sodium bicarbonate, and it also dissociates into the sodium ion and the bicarbonate ion. So this is the reaction, this third one, that you will measure the change in enthalpy of. But what we want is the heat of reaction, the change in enthalpy of reaction for solid sodium bicarbonate reacting with solid citric acid monohydrate, this third reaction right here. And so using Hess's law, if we can get the heat of solution for the acid, heat of solution for the salt, and heat of reaction for this third one here, then when we add them up, it should give us what we want. You guys see that? How that adds up like that? So our heat of reaction for the solid citric acid monohydrate with sodium bicarbonate is going to be equal to the heat of solution of the acid plus 3 times heat of solution of the salt, because of this 3 right here, and the heat of reaction that we measure. So let's go through that. I'm going to give you some numbers that you're going to use your own numbers, right? These are just my own numbers. So first, let's look at the heat of solution of the citric acid monohydrate. The change in enthalpy of solution for that will be just the Q of solution over the number of moles. Q of solution of the acid is going to be negative Q of the water plus Q of the calorimeter. Q of the water is ms delta T of the water. Q of the calorimeter is the calorimeter constant times the delta T. Remember, we figured out our calorimeter constant in part A, the first part of this experiment. And then N over here is just the grams divided by the grams per mole of the citric acid monohydrate. So for example, here are some numbers. Again, do not use these numbers. Use your own numbers. All right, so I'm going to do these calculations right up here. And using these numbers right here. So let's say I did the first part of the experiment and I got my calorimeter constant. Yours is going to be different than this, don't worry. Anyway, so Q of the solution is negative Q of the water plus Q of the calorimeter. Q of the water is the mass of the water, specific heat, 4.184 times delta T of the water, plus C of the calorimeter times delta T. When I plug those numbers in, I get this right here, and it ends up being positive about 220 joules. Finding the moles of the citric acid monohydrate, I take the grams that I had divided by its molar mass. Got that many moles, dividing the Q by the moles, I get my delta H of solution for citric acid monohydrate. And with my numbers, I get about 32 kilojoules per mole. Now we're going to do the same thing for the sodium bicarbonate. Same idea, Q of solution is negative Q of water plus Q of the calorimeter. I use the same calorimeter constant. So let's use these numbers. These are the mass of the water, the mass of the salt of the sodium bicarbonate, the initial temperature of the solution, final temperature of the solution, water, so on, and the same calorimeter constant. So Q of my water is going to be ms delta T. I get a negative 260 joules or so. Q of the calorimeter constant times delta T, I get a negative 78 joules. Q of the solution, that is negative the sum of those two, which gives me a positive roughly 330 joules. Number of moles of my sodium bicarbonate is my mass over its molar mass. I get that many moles. Dividing the Q by the moles, I get my delta H of solution, which is about 17 kilojoules per mole, with my numbers. And then we get to the reaction that we measured the delta H of, the third part here. Same idea, really. Delta H of reaction is a Q of reaction over the number of moles. N is the number of moles. Q of reaction is negative Q of the water plus Q of the calorimeter, and the moles is the grams of the limiting reactant divided by the molar mass of the limiting reactant. Now you should do the calculation, figure out what the limiting reactant is. With my numbers, it ends up the limiting reactant was the citric acid monohydrate. Notice that the number of moles of citric acid monohydrate that I weighed out is the same as the number of moles of the aqueous citric acid, because I get one of these from one of the monohydrate. Q of the water, Q of the calorimeter, so on. So let's use my numbers again. Use yours. There's the mass of my water, mass of my acid. This is the solid citric acid monohydrate I weighed out, but the moles of that will be the same as the moles of the aqueous citric acid. Moles of my sodium bicarbonate, that's a salt, initial temperature, final temperature, and the same calorimeter constant. So my Q of reaction is going to be negative Q of the water, MS delta T, plus Q of the calorimeter, C calorimeter delta T. When I plug those guys in, I get about a positive 580 joules for my Q of reaction. Again, for me, my numbers, the limiting reactant was the citric acid monohydrate. It's that many moles. Again, you find your own limiting reactant. It depends on your numbers. And whatever it is, that's what you use here. Dividing my delta H, my Q of reaction by the moles, I get my delta H of reaction, which I get about 120 kilojoules per mole. So this is the delta H for the reaction between aqueous citric acid and the aqueous bicarbonate ion. What we want is this right here, the heat of reaction for the reaction between solid citric acid monohydrate, solid sodium bicarbonate. And remember I showed up earlier, that's just equal to the heat of solution of the citric acid plus 3 times the heat of the solution of the sodium bicarbonate, the salt, plus the heat of reaction that we just calculated. Plugging those numbers in, adding them up, I get about 200 or so kilojoules per mole. And there you go, that's how you do it.